Okay, so in problem number 9, we're asked maximum, it just happens to be multiple choice, maximum permissible exposure values for lasers are given 4 different durations. You may remember the table for that. Let's see if I have it handy. Here we go, different laser types, different wavelengths of exposure, different times of exposure for the maximum permissible exposure level, K watts per centimeter squared. And you can see for they're different based on the time of exposure and the power level on that laser and the wavelength of that laser. So I'm going to put that away for now. Just keep that in mind. So for laser given in 4 different durations, as we saw, quarter of a second, 10 seconds, 630,000 seconds, what did the different time durations correspond to? Okay, so let's read the first one. Maximum permissible exposure limits indicate the greatest exposure that most individuals can tolerate without suspending injury, expressed in terms of the allowable exposure in seconds at any wavelength. Well, that's not true. It's different for different wavelengths, so that's not going to be a correct answer. Let's go down to this bottom one. Maximum permissible exposure limits indicate the greatest exposure that all individuals can tolerate without sustaining injury, expressed in the allowable exposure over an 8-hour workday. Again, it ignores the type of laser, the wavelength, and so on and so forth. And it's not necessarily an 8-hour workday. We have exposure limits for shorter durations, also down to a quarter of a second. So that's not the right answer. And let's calculate. Let's take a look at this one. Maximum permissible exposure limit indicates the greatest exposure that most individuals can tolerate without sustaining injury, expressed in terms of the allowable exposure in seconds, they're all in seconds as it happens, for a given irradiance in watts per centimeter squared at a particular wavelength that particular laser operates. So that one's nothing is not true there. So that one is okay, and none of the above is false, of course. In problem number 10, we're asked if a researcher is using a krypton 0.568 micron laser in a lab operated at 75 watts, the power level is 75 watts. What's the maximum permissible exposure for a 30,000 second duration? Assume the initial diameter of the coherent light is 2 millimeters with a divergence of a spread of 2 times 10 to the minus third radius. Very small spread. That's almost doesn't spread out at all, but it's a very small spread, but it's significant. So radiance has no units. The initial diameter is 2 millimeters, and we have seconds, and the power that we're operating is watts, and we have a specific kind of laser that we're working with. Okay, so in this case, let's take a look at how we would determine what the maximum permissible exposure limit would be. So
this conference will now be recorded.
Okay, so let me pull up that table again. So for a krypton 0.568 micron laser, krypton 0.568 wavelength of laser, for 30,000 seconds, the maximum permissible exposure limit is 18.6 times 10 to the minus 6 watts per square centimeter. That's the maximum permissible exposure limit. So that's basically all they're asking for in that particular problem, but this is going to carry over to the next problem. So in the previous problem, we looked up what the maximum permissible exposure limit was for 30,000 seconds for this particular laser. So now we're interested in knowing, well, what is the hazard exclusion zone, nominal hazard exclusion zone that we need to protect the worker if he's not wearing a PPE. So there's a few formulas that are involved here, and we got to decide which one that we're going to use. Let's find them here, and here we go. Okay, so nominal hazard zone, the space within which a level of direct contact, reflected or scattered radiation exceeds the MPE. In other words, within that zone, you can exceed the maximum permissible exposure limit. Outside of that zone, you're not likely to be exceeding it. So we're going to define that distance. Okay, so these formulas, now one of the issues here, is that there are different situations that you might be measuring this in. Do I have it here? Let's see if I have it here. Okay, so we could be measuring it in a situation where it's a direct exposure to the beam, like this first area here. It could be a reflection or from a mirror or some other surfaces that we could be dealing with, or it could be a reflection from diffuse surfaces, surfaces that are not good at reflecting the laser beam, or less efficient at reflecting it. Okay, in which case you've got to be concerned about the angle and so on and so forth. So we have three different formulas for this situation. We have the first formula, which is direct exposure, which is most hazardous. We have the second one for reflective surfaces, and we have the third one for diffuse surfaces. Okay, so we didn't define that here, so we're going to assume it's the most severe case. So we don't need the other functions here that describe the surface and the focal length and so on and so forth. We're just going to be using this formula here. So let me get rid of this so we can see. And I think I have this formula in a form where we can see it a little easier. If I can find it again, problem. Hopefully your calculations are going to come out same as mine. Our hazardous zone is going to be equal to 1 over the beam divergence in radius. This is unitless, which is 2 times 10 to minus 3. Okay, times our power level, 4 times our power level of our laser, 4 times 75 watts, over 3.14 times our exposure limit, which was 18.6, I believe it was. Let me just make sure of that. Nope. There we go. Is 18.6 times 10 to the minus 6th. To the minus 6th. Okay, minus the beam diameter, starting beam diameter, which is very small. It doesn't spread out very much. It's very small diameter. It's 0.2 millimeters. I'm going to convert that right now. 0.2 millimeters is the same thing, 2 millimeters is the same thing as 0.2 centimeters. It was 2, right? Where is it? Where is it? 2 millimeter diameter, initial diameter. 0.2 centimeters. Okay, so it's a squared. 0.2 centimeters squared is 0.04 centimeters squared. It's going to wind up being negligible probably. So let's actually go ahead and calculate this. I'm going to clear this out and clear out memory. So my denominator here is going to be 3.14 times 18.6. Okay, is equal to that. I'm going to move that into memory. And I'm going to clear that out. I'm going to ignore the 10 to the minus 6 for now. I'll deal with that later. And our numerator is 4 times 75 is 300 watts divided by our denominator. Recall it now. And that's equal to 5.13, et cetera, et cetera. Okay, except now we've forgotten about the 10 to the minus 6. That comes up to the top, becomes 10 to the plus 6, okay, times a million. Okay, 1 million. Okay, so our this part of our formula is 5,136,000 minus 0.0, and that's in square centimeters, right? Because this was watts per centimeter squared. Watts cancel out, so it's centimeters squared. This is just centimeters squared, so I'm subtracting it. It's negligible, so I'm not going to bother with it. However, now I have to remember this is to the square root. This is square root of this whole thing to the 1/2 power. So I'm going to go back to my calculator. I'll take the square root of it. Okay, and the square root of it is 2266 centimeters. Okay, so that's how many centimeters that this whole expression represents. It's centimeters because the square root of centimeters squared. This is unitless, so it's going to stay centimeters when I complete the operation. So I'm going to divide that by 2 times 10 to the minus 3, which is divided by 0.002. And that's equal to 113,000, excuse me, 1,133,207 centimeters. So I'm going to go to Google, as I have so many times here, and I am going to find out the answer in feet. So centimeters, whoops, I did that wrong, I think. Oh no, I'm okay, right? I pasted that in. 37,179 feet is the distance we would have to be to not be harmed by looking directly into this laser from without protective equipment. So that's our nom for 30,000 seconds. So that's our nominal hazard zone for this exposure. 37,179